Ladies and gentlemen, my name is Alexander Reitholz. I'm a PhD student in Sorbonne University. I'd like to present today about vapor-liquid equilibrium of hydrocarbon and mixtures, and also other topics, recent topics about non-random lattice fluid equations made with hydrogen. This work was supervised by Professor Kiko Yu, Jung from Lim, Professor, and Jae-do Kim from KISS, and Professor Kang from Korea University. The motivation for this study is we wanted to use brightness factor for lattice fluid equation of state instead of binary interaction coefficient. Because brightness factor in theory can be fitted on a zero component. We have introduced the temperature dependencies for the lattice volume size to reduce also binary real binary parameters. And we're trying to extend the calculation from the lattice fluid equation to supercritical region. I will present some results today. And of course, we obtain hydrogen bonding parameters for amine systems. So the results will be that we have obtained brightness factors for various constants. We have done some supercritical correlations, and the hydrogen bonding parameters. What data did we use for our calculation? Mostly we use electronic version of the Dortmund data bank and the Korean data bank. And in this study for amine system, we have also used experimental data. Usually, we calculate VAE detail with the temperature range about from 200 to 450 Kelvin, and low, medium, and especially now also high pressure. And we usually do this with VAE data sets. So I will just very brief. The basic framework of non-random lattice fluid equation of state. This is the size coordinate number contribution. This is we're using the original equation of state is the Kingsford potential. And here we introduce the lattice volume with temperature dependent with 3 parameters. The molecular parameters are segment length and energy parameter or temperature dependent and the brightness factor. This is the surface area reflection balance. So here in this figure, you can see the temperature dependent of the energy parameters, and this figure shows that the derivation changes from low carbons to higher carbons. So this is this behavior is not very good for prediction and calculation because it goes from negative to positive values. So this is calculated without brightness factor, and when we introduce brightness factor, we can reverse this term, so the derivation is always negative in this way, and this makes calculation more easier and more stable. This is also the lower carbon and the higher carbon multiplied by C1 to C10. And the temperature against the energy parameter. How did we choose the brightness the correct value of the brightness factor. Right now this cannot be done automatically, so we have to select the brightness factor by some criteria. And one criteria is the error of the calculation for the pure liquid density. This is the black dotted line. And pressure derivation for VLE data with hexane. Hexane is our reference component. We choose hexane with a brightness factor of 5.9, minus 5.9. And here we can see the vapor composition for VLE data with hexane. So the density deviation shows that the minimum may be at point with a brightness factor of 4, but the VLE calculation shows that it would be better for VLE correlations to choose a little bit higher brightness factor. So this is how we choose try to set the brightness factor. We sacrifice a little bit of pure liquid density, a little bit of accuracy we sacrifice to obtain more correct VLE correlations. This is the obtained parameter overview. Here's the brightness factor for various components, and here is the reference component, same, 5.9. This is the error in the pressure range. You can see the error is quite low for most components. These are the volume and size parameters for the fluid rotational state. In this study, we calculated for amine. So we try to obtain hydrogen bonding parameters for several groups of amine. We divided them by primary, secondary, and tertiary components. And we have obtained 3 different sets of hydrogen parameters. Hydrogen bonding parameters are usually only needed for polar or weakly polar components. So here are the results for subcritical mixture calculation. For this, here's the system name and the temperature, and here. Here's the calculation without binary interaction parameter, and the error in the pressure range is about 1, or in the region of 1%. And we can, it's possible to introduce the binary interaction parameter and fit this parameter. It's possible to get even better results in the pressure range. The binary interaction parameter is very slow, so we think that this error might, we can sacrifice one parameter fitting. We can live with this error because maybe the experimental data has also the same error range, about 1%. So this would be a good way to eliminate one binary interaction using temperature dependencies of the lattice volume size and the brightness factor. And here's also the calculation for Wong-Sendler. Hang-ons and Wong-Sendler mixing group. The results are quite good, but you have to keep in mind that they use a lot of parameters. You have to always pick 3 parameters for one calculation. Here's comparison of Pico and temperatures. The results are all look quite similar. So 1% error does not make a big difference when we see the whole picture like this. Here's NFA calculation with binary interaction parameter and without. Both are quite similar. This is another example. You can see the results are always quite similar, so we think maybe. And it is not enough to assume that we can, at least for medium, lower and medium temperature, we can avoid the binary interaction parameter. So I like to take now go to amine system. The correlated data set for hydrocarbon-amine and heptane was supplied by Mr. Kim, and the other data were taken from KDB and broken data there. Here's the overview of the system. The hydrocarbon-amine system was isobaric. The measurement was isobaric. So when you compare that always temperature levels, temperature and the pressure for calculation. This is hydrocarbon and heptane, and without binary interaction parameter, just fitting hydrogen bonding parameter and brightness spectrum. The results are quite promising. This is done by one bar. This is for hydrocarbon and hexane. 0 degrees Celsius. This is for hexane and hexane. Hexane is always the reference component, so we like to choose always the reference component when we calculate first, because we know the brightness spectrum of this component. This is methylamine and hexane. And all data looks, fitting looks quite okay, only this week, but maybe this can be done in the future with adjusting more to a little bit slightly the hydrogen bonding parameter. And this is hydrocarbon and hexane. I'd like now to move on to present some results about supercritical calculation. The problem with supercritical calculation is that they get very unstable near the critical point of the mixture. So there is a need for adjusting the size parameter in the supercritical region. And unfortunately, for supercritical calculation, we have to introduce again more parameters, like again introducing the brightness spectrum, which we can avoid for lower temperatures, but for higher temperature in the supercritical region, there is no other choice. Here are the parameters for methane and carbon dioxide for in the supercritical region. And here are the results. So we used again the binary interaction parameter, and the pressure range, the data for the supercritical region is also not considered very accurate. So in future we think that the results, when we look at the average of 2%, in future the average calculation will be more trustworthy. Here, in comparison, there's a Ping-Robinson calculation without wrong standard mixing rule, because wrong standard mixing rule, I said already, needs 3 parameters for fitting, and 3 parameters in supercritical region are very difficult to fit at one time. So we use only Ping-Robinson calculation. Ping-Robinson calculation. These are we work on methane, and in methane, the temperature of 510 Kelvin. You can see the results are quite good. And there's a slight problem near the critical point, so we usually skip the exact critical point of this solution. And dioxide and ethanol, usually when we calculate, the trend is like in equational state, it's always a little bit lower than the actually critical point of the mixture, and the lattice fluid equational state of hydrogen bonding always keeps a little bit outside this region. This is what this figure shows. The lattice fluid equation goes a little bit outside. So actually, equilibrium plates and penguins always keeps a little bit on the inside. So I like to make a short conclusion. With hydrogen bonding parameters for amine, the lattice fluid equational state can represent via ideator, quite nicely. Supercritical calculation require more parameter, introducing more parameter, and some adjustment to the size parameters. And with introducing temperature dependencies to lattice volume size and brightness factor, VAEDAT can be correlated, and the aim is to reduce the needs of binary interaction parameters at least at low and medium pressures. Or when we introduce binary interaction parameters, they have no very small value. If you remember the first slide of mixtures, I showed you the binary interaction parameters are always in the range of 0.005. Like this. Yeah. Thank you very much for your attention.